Haqq-Misra, and then we will finish on some open discussions.
Okay, thank you for, let me move this over there. Okay, I'm assuming everybody can see that. Thanks for sticking around to the very end. So I'm going to tell you about samosa, which these are dessert samosas for today. But in any case, we have a great number of people participating in this so far. I'm sorry if I missed your name. I think I got everybody. But for samosa, just to mention, this is also kind of derived from the Champs ICAR funded team, as well as being part of cuisines. So here is our timeline. We kicked off officially samosa. We had the protocol paper a little bit before that, but at last year, um, after buffet, we formally started, having regular monthly meetings. I won't say they're actually monthly, but we have a scheduled monthly meeting at least on the calendar, and then we meet, when we can and when it makes sense to. So we had our kickoff meeting. We did publish an erratum, and here we are with some preliminary results at BUFFET-4. And then we hope for next year to be, have something like complete results where, most of the cases by the participating models are in. And then, we will, at BUFFET-6, we'll, aim for having the analysis papers finished. If we don't hit this timeline exactly, that's fine. But at least it's a goal. So just as a review for everybody who might be new, the main motivation for Samosa is comparing between these, fast, computationally inexpensive models, which you can explore a broad parameter space with. These might be energy balance models, radiative convective models, all kinds of models that are quick and easy to run, but maybe you're sacrificing accuracy or you're parameterizing certain features. So how do you compare those results to these more computationally expensive GCMs where you can't necessarily run hundreds or thousands of cases very easily? And so what motivated this was a paper by Deep Paradise, who's actually here, which is great. There was this paper, Exoplasm, Extending the Planet Simulator, has many, many different simulations in it, but we focused on this one, which is looking at a synchronously rotating planet in a fixed 15-day orbit, rotation rate, around a 3,000 K black body star. And all the dots here are simulations. There's, I think, 460 of them. And so this is with an intermediate complexity GCM. So it's relatively fast to run and you can do hundreds of calculations. And so we have this, there's other variables I don't show here, but we have average surface temperature. You can see there's cold climates to the right where there's low installation. There's warmer climates to the left where it's higher installation, and then surface pressure increases from the bottom to the top. And in this paper, the authors are not claiming that this is the correct answer. This is what the model produces, and as we've talked about, none of our models may be correct, but we want to compare them. And certainly, when you use an intermediate complexity GCM, you're making some simplifying assumptions with radiative transfer and maybe some other physical properties. And so the question is, how do results like these compare with more robust GCMs? And how can we do that without having to run 460 cases to compare the two? And so what we do is we use sparse sampling, which we can talk about later if you have more questions. But we actually pick 16 cases. They're intentionally concentrated to the right of this side where there's the colder and more temperate cases. On the left, where it's really hot, we tend to expect the cases to be more numerically unstable. These may be runaway cases, physical runaways or just runaways in our model, but in any case. And I've highlighted in blue case 4. And so the goal of SAMOSA is for all the participating models to do what you can. We understand that even 16 cases with a computationally expensive GCM might be time consuming depending on your model and your human resources. We focus on case 4, which is probably the most temperate of all the cases. And so what I'll show is some preliminary results from comparing case 4 as well as the models that have run all the cases. And so this is from the protocol paper. In the protocol paper, we did show some preliminary results just with exocam, and then exoplasm on the right side here from the paper that was previously published. And so this is just a kind of a really schematic comparison where I've binned the different results. So you can see there's actually general agreement when I bin it like this. If you look at the exact average temperatures, of course, there's more differences, but exoplasm and exocam generally agree on, what's icy and, the one of the warm cases, this case number 4, with what exocam has, that's also shown in exoplasm. The 2 hot cases at around 1500 watts per meter squared are both predicted to be hot by both models. And so the main difference is, which ones are runaway or numerically unstable cases. And so just again from the protocol paper, here's a sampling of some of the cases that were stable. And you can see we've got cold cases, some temperate cases, some very hot cases. You can see SAMOSA 4 here has an average temperature of 260. You can see the substellar point is fairly temperate, and so that's one that we'll focus on. But that's kind of where we were at, after publishing the protocol paper. And so you don't have to read all this. This is just to say we, in the last year did publish an erratum. They were kind enough to not require us to do a full paper. And I'll just mention this in case you're thinking about participating, but you haven't. The main error was that we had said use a fixed mixing ratio of 400 parts per million of CO2. That's wrong. We want a fixed partial pressure, 400 microbars, because the pressure is changing with each case. And so if we kept the mixing ratio fixed, some of them will have proportionately more or less CO2. So we want to keep the partial pressure of CO2 fixed, which is the same that D Paradise did in his simulations. And then some other case, just make sure you're using a warm start, and then we specified global output quantities. So you can find the erratum if you're going to run the cases. Just make sure you look at that. So since then, in addition to working on the just conducting the simulations, we were also trying to think about how do we analyze these sparse samples. And we learned that it's not very easy to use conventional interpolation techniques for coming up with a contour plot when you have sparse samples like this. Conventional interpolation routines tend to like large numbers of simulations, but also when they're on a regular grid. And so even though these are distributed in a uniform way, there's not a uniform distribution. It's a uniform coverage, but it's a stochastic sampling. So what we did, and I won't get too much into the weeds of this, but we use a method called kriging. It's kind of related to Gaussian process emulation, but this is really for sparse samples. And so we're not trying to emulate necessarily, although we could go in that direction if we wanted to. And just the short explanation here, as you can see from number 0.3, I've got 2 vectors going to 0.7 and 0.12. This is h. This is our distance, right? Our spatial separation. And so what you do is you calculate the spatial separation between all the pairs of points, and then you calculate the dissimilarity in value of temperature, which is the value squared divided by the spatial separation. I'll mention that this method was originally developed for geostatistics, specifically for mining, for drilling on a field looking for gold or other ores. The problem is you want to do a sparse number of drill core samples and then get some idea of what the underlying distribution is of your resource. But in this case, the drill cores are sparse sample. The average surface temperature is our ore, and you can use this for a wide number of problems, and it is very widely used in other astrophysical and earth science problems. And so the variogram on the right is just showing, you essentially make a histogram of spatial separation versus dissimilarity, and then you fit a line or a curve. It can be a number of different functions, whatever makes sense. And then that gives you a measure of how the values change across the domain. And so once you have the variogram, then what you can do is you can predict what the values should be at the other points. And so on the left here, you can see I've circled in black the points that we've actually calculated. And then you can use kriging once you have this variogram function, you can then predict what the values should be, according to this function, at other points on your domain. Once you've got this nice, regular gridded set of Krieged points, then you can use an interpolation method and you can get contoured like we want. And so you can see on the right, we've got cold climates on the right side of the right panel. We've got very, hot on the left, and then this intermediate transition zone. You can see there's this is with the exocam value results too. You can see that at around 1500 watts per meter squared at higher pressure, there's, some kind of funny looking places where, perhaps is the more interesting area to look at and see what's the model doing and how do different models represent this transition. And so that's our analysis paper. So coming into our preliminary results here, we have 5 models, including the original exoplasm cases. So you can see they're all numbered on the upper left. Exocam has completed all of the cases. The X's are the ones that are unstable in the model. You can see Rocky 3D has also completed all of the cases, which with 3 of the Rocky 3D cases did reach some stability, at least nominally. And then there's one with a plus that I think Chris Close said is still running. And so the jury's out if that one's going to be stable or not. We have generic PCM. Now, Siddharth did send me some new cases that him and Guillaume, I think, have been running with generic PCM with and without dynamic ocean. So I did not have time to include those in here, but those will be included soon. And so generic PCM has run just case 4 so far. And then Plahab, Ramses Ramirez, is using a 2-dimensional energy balance model to participate, which is great. And so he's run case 4 so far already. And so with the energy balance model, you don't have all the same outputs that you do with the GCM, but that's fine. Whatever model you have that you want to participate with, we can work with it and we will compare whatever outputs we have. So to compare the 2 cases that have the full 16 set of samples, we've got Exocam and Rocky 3D, and you can see there's obviously some similarities here and some differences. And this is again using the Kriging interpolation method that I showed earlier. And so you can the cold cases agree fairly well. Rocky 3D has a larger sort of temperate region shown in the green compared to Exocam. And, 3 of the cases are consistently numerically unstable runaways between the 2. But there's certainly some interesting work that we have to do to understand, why are some of these more stable in Exocam versus Rocky 3D. And this could be just, basic parameter functions within the model itself. They may not be revealing physical properties of the planets, the hypothetical planets. But this is at least promising to show that we're already learning something. So hopefully next year I'll have this panel with many more, at least a few more models to show how they all compare. If we want to look then at, I showed you the variogram earlier. This is just how is the spread of data different? And this is for all 16 cases. So if I'm calculating the variogram for Exocam, the variogram for Rocky 3D, we can just look at this in case it's useful. This is just because we can plot this. And really the take-home message here is there's just less spread in Rocky 3D compared to Exocam. As the points get further apart on your domain, there's greater dissimilarity in Exocam than in Rocky 3D. And so, in some ways, this maybe just checks your intuition when you're analyzing the plots too. So as I mentioned, we're focusing or at least initial analysis on case 4. And that also just provides an entry point if you're new to participating in SAMOSA or if you have limited time, we can just do case 4. So case 4 is 1200 watts per meter squared installation and a 2.34 bar surface pressure. And then on the right, I've just shown the parameters that are constant for all the simulations, reminding you that it's a microbar, not parts per million for CO2, but it's an aquaplanet, 15-day orbit rotation period, and otherwise it's an Earth-like planet otherwise. So here's some global mean statistics for the 5 participating models. Exocam, exoplasm, generic PCM, Rocky 3D, Plahab. So they all get warm climate conditions in a general sense. So there's not, strong differences in terms of one being an ice ball and one being largely ice free. That's good. There's a bit of a spread between, if we look at mean temperature, exocam, exoplasm around 260, same with Rocky 3D, generic PCM a bit warmer, Plahab a little warmer. Now, again, I mentioned there are new generic PCM cases I haven't plotted, so don't hold them to this. This might change. I haven't even really calculated these with the new data they sent me. But you can look at the max and min, at least in this set, the maximum temperature for generic PCM is actually quite a bit more to the rest of the models compare pretty well, around 300. And for minimum, um, the Plahab, the EBM actually is the warmest in this case, although generic PCM is also fairly warm. But you can see part of the difference here is the ice fraction. So we're at about 70% ice coverage for many of them, except for generic PCM in this case. And then stratospheric water vapor content. Exoplasm is the driest. That's not surprising because that's one of the known limitations of that intermediate GCM. Just the lack of ability to do a robust runaway greenhouse, moist greenhouse simulation. So with Exocam, we've got more water vapor in the atmosphere, a little bit less for generic PCM and Rocky 3D. And then, of course, Plahab being an energy balance model, that's a quantity we don't get. We can look at surface temperature and winds. And, structurally, these look pretty good. You've got, this is just on the surface. I didn't show the elevated winds, but you have, wind, flow coming in to the substellar point, presumably then rising and moving aloft and outward and to the night side. The day side substellar temperatures and region covered by the substellar point are pretty similar, but you can see the differences in the temperature of the night side. You can see these sort of cold vortices here toward the night side terminator area are more pronounced in exoplasm and Rocky 3D. You see them a little bit in exocam and not so much in generic PCM. And then Plahab is perhaps the warmest and most uniform across the whole domain. Again, there's no winds in Plahab, and this is interesting to have both 3D and 2D models participating in this. One of the results we hope to get when we do the analysis paper is, where are the parts of the parameter space where the simpler models are just as good, or at least, in agreement with the more complex models, and where are the parts of the parameter space where you really need the more complex, computationally intensive models to have some, to believe that you're making any sense of your results. We can look at outgoing long wave radiation. So you can see structurally some similarities. Rocky 3D. I have to check if I flipped something around, but maybe not. So I have to look at that. If it's really truly that Rocky 3D has in sort of this inverted C shape, or perhaps that's just a plotting error on my part. I think it might be. Because the others all agree sort of with this, open Pac-Man facing shape, chomping toward the right side of the plot. You can see generic PCM has higher OLR all the way across the equator. You see that feature to some extent with Exocam, but not as strong, and same with Rocky 3D. And then not at all with Plahab. You just have the highest OLR in the substellar point, and then much lower on the colder parts of the planet. And so this is, I can show again a variogram. Now, the earlier variogram I showed was comparing Exocam and Rocky 3D across the whole parameter space. You can do these though with any set of data across any domain, which is what's fun about kriging. So in this case, I'm showing just this plot. I'm just showing temperature itself. How does the temperature variable change across latitude and longitude for each of the models. So if we do that, you can see ExoCam has the greatest spread of dissimilarities as you move from one point to another. Plahab has the least. You notice that the shape of this variogram is a curve, an exponential type function instead of a line. And that's just what, part of the kriging method, which we can talk about later, is there is a human element of analysis. You can't fully automate it. You have to actually inspect the data and make a judgment about what variogram function makes sense for that particular case. And so in this case, the exponential gave a more meaningful result. And so again, this kind of is a way to check your intuition about, when you visually inspect the temperature plot, you can see which models give you more and less spread. So yeah, I think that is all I have. So please, if you have not joined our intercomparison yet, but would like to, you're welcome to. Participation will remain open for at least another year before we, try publishing anything significant. We're going to just keep having our monthly-ish meetings, analyzing case 4, analyzing the full set, and kind of just building up essentially our first analysis paper that way. By the time a year has gone by, we should have a full set of plots that we can put into at least one paper. And then just to mention, you don't have to do all 16 cases. You can just do the warm case. You can just do the 8 cases that are what we call sequence 2. If you look at the protocol paper, you could just do the ones that ExoCam found to be stable. You could do all 16 cases. And then I didn't show in this talk, but if you go to the protocol paper, we actually have additional sequences that have more points drawn across the parameter space. So there's actually up to 64 model runs that you could do if you would really want to. So we don't expect everybody to do that, but that's an option that we have. I'll mention too, I did get a Roses grant funded with Thomas, where I'm going to use an energy balance model, a 1D energy balance model, but trying to do this configure the energy balance model. So instead of doing latitude, it's doing this tidally locked, synchronously rotating coordinates where you're trying to capture the day-night temperature profile. And so I'm going to attempt to do that. I'm going to use probably ExoCam to tune it. And then with that, it's an EBM, so I'll easily be able to run all 64 cases. And we'll see where that goes. But EBMs are welcome. 1D radiative transfer models are welcome. Whatever you want to do, we're certainly willing to work with you and see where it goes. So that's what I got. Thank you.
Awesome. Thank you very much, Jacob. That's super interesting. Do we have questions and comments from the audience? I know we have the one from Adiv. Adiv, do you want to take it out loud or should I?
It was not so much a question, more just in that first plot, Jacob mentioned that there's a disagreement between exocam and exoplasm in the runaway region. And in exoplasm, if I remember correctly, it doesn't run away, but I did find high stratospheric water vapor in those models. So it's just a note, like when you're doing GCM simulations and intermediate complexity, lower complexity stuff, it's always worthwhile looking for multiple diagnostics to see if your model should be running away, even if it doesn't actually have the physics to do that.
Yeah, excellent point.
Dennis?
I have great talk, thank you. I have a small question about sort of model failures and how sort of permissive you are in your protocol. So for example, if you imagine a situation when a GCM can do a bunch of cases, but then at the boundary with the high radiation regime, it fails, so it goes into a runaway state. But then maybe, like, first of all, at what point should you kind of stop trying to make the model stable? And also, if you can find a configuration that is kind of more stable for that particular case, would you still accept it as sort of the same model, or should we keep the sort of basic configuration of the model the same across all the cases?
Yeah, that's a great question. One of the, sort of, I'll call it cultural differences between this intercomparison and the others is, yeah, we're not so much trying to configure the models exactly the same and then see where the differences are. We are usually modeling the same planet, and we do have a set of obviously, parameters that you have to fit in order to, a set of configurations you have to do to actually run those cases. But beyond that, put your best model foot forward, or I think Eric said, come as you are to SAMOSA, right? So if if uh, if you find a way that you can do certain cases, you just be verbose about it. Just when you're sending me the results, you just explain to me what's going on, because that's an interesting result. If you find that you can run 10 of the cases with the standard configuration that you usually do, but then changing some convection parameterization, say, allows you to make these runaway cases more stable. Well, that's great. That's fine. We can very easily incorporate that into the discussion of the paper. And yeah, we're more interested in just seeing what your model can do when you use it the way that you want to use it. There's also value, when I'm part of Fillet. Fillet takes a slightly different approach for many of the cases where most of the experiments are sort of not really the way most of us would run our EBMs. And they're not even really like real planets in a sense, but it's forcing the models to all have as close to the same configuration as possible in Fillet, for the purpose of seeing where their differences are. And I think that is really useful for Fillet. But in this case, yeah, it's more about how well can each of these models explore the parameter space. And so it's perfectly fine to have differences even within your own cases, as long as you just explain to me so that I'm not guessing what's going on.
That's great. Thank you.
Thank you. Do we have any other questions, comments? I have two actually. So first one, so Jacob, can you explain why the Kriging approach, why previous attempt with the more standard approach were not satisfying?
Why Kriging instead of regular interpolation?
Yes.
Uh, it just doesn't work. We tried. Regular interpolation tends to work better with larger samples, but really it needs a regular gridded distribution of points in order to work. Otherwise, you just get really wonky results. I don't have the figures up here, but Eric did a nice job where he actually explored, a dozen or so different interpolation methods. And yeah, they really don't work well when you have sparse points that are irregularly distributed across your domain. And I guess I'll mention too, I showed only two-dimensional plots with Kriging, but Kriging works on an arbitrary number of dimensions. You could do this with a sparse number of samples with 10 dimensions if you wanted to. And so that's, we haven't fully explored that yet, but it's certainly something that we can do. And so that's one of the powerful benefits of it too.
Sounds good. Thank you. Kostas?
Jacob, I'm just piggybacking on that same question. I might have asked you in the past, how have you selected the sampling, the samples? Was that like Latin hypercube approach or something
Oh
like
yeah,
that?
great question. It's a Sobol sequence. It's quasi Monte Carlo selection. The only reason that we didn't do Latin hypercube, they're very similar. With Latin hypercube, you decompose your domain into sort of set of a grid or a set of boxes, and then you're sampling so that you tend to get 1 point per grid. So it's stochastic, but it's still got some uniform type properties. And the only limitation for that is it's not easy to then extend the sample. If you want to extend the sample, you have to regrid it and draw a new sample. But for quasi Monte Carlo, we can actually extend it arbitrarily. You just have to do it by powers of 2. So that's why in the protocol paper we have multiple sequences. So sequence one, we drew 8 points. Sequence two, you drew another 8 points, and then when we extend it, you can do 16 and then 32 points. So obviously at some point it gets very large, but you can you can extend you can add to the sample without having to redo anything, and so that was mainly the reason.
Okay, but it really calls for an emulator, you know.
Kriging does not require an emulator.
No,
I
it
mean,
doesn't require it, but it can
yeah.
give you more information for the gaps in between, and you don't have to worry about interpolation because you can use the emulator to fill in the gaps yourself.
I mean, it's no different. Like the interpolation is just for making plots, right? So when you do kriging, you can so right. So if you do kriging, you can fill in the points, but you can then add more points to decide, I mean, this is how you do the emulation actually. You could draw more points and you can check how good was the kriging interpolation. But then if we've drawn more points, then you can add those to your sample and then you can interpolate in those. So yeah, there's sort of an infinite number of times you can do that, or not
Right.
infinite, but you can keep going as many times as you have resources for.
Thanks.
So I have another question. Okay, so when I saw your plot with the dissimilarity as a function of the GCM, I was wondering if that could be interesting to ask each of the the GCM output, what was the level of convergence of the GCM? Because I know that depending on the GCM, we have more or less the energy balance is not necessarily at the same level. I know that, for example, here, correct me if I'm wrong, Costa or Linda, but for Rocky 3D, usually you try to achieve 0.2 watt per meter square in terms of energy balance. Sometimes some other group do like 1 watt per meter square. So I was wondering if this affect the level of dissimilarity. It could be interesting to put the number here along with the curve.
Yeah, that's a good point. We should do that.
Yeah, awesome. That's why it's important to have those meetings, see?
That's right.
Because I'm very familiar to this data with just seeing the plot. I just like,
Yeah, totally. That could make a difference for sure.
Great. Any other question, comments, or should we move to open discussion if there are any? We already have a lot of discussion these 2 days after each talk, so I don't know if you all have still some